Welcome to Lecture 5.3, Examples of Group Actions. Obviously, we've seen a number of examples of group actions so far, but the focus of this lecture is the action of a group G on either its elements, its subgroups, or cosets of some fixed subgroup. Sometimes the orbits and stabilizers of these actions are actually familiar algebraic objects. Also, sometimes a deep theorem has a slick proof via a clever group action. For example, in this lecture we will see how Cayley's theorem, recall that means that every group G is isomorphic to a group of permutations, follows immediately once we look at the correct action. Here are some common examples of group actions that we will look at. First, G acts on itself by right multiplication or by left multiplication. So here, G acts on a set S, and the set S is also G. Or G could act on itself by conjugation. So it's the same group, same set, but a different action. G could act on its subgroups by conjugation. Here the set S is the set of all subgroups of G. And finally, G might act on the right cosets of a fixed subgroup H by right multiplication. Or, of course, we could do the left cosets by left multiplication. For each of these, we will analyze the orbits, the stabilizers, and the fixed points. Let's start by groups acting on themselves by right multiplication. And we've seen this in the first lecture in this series. Well, this action is boring because any Cayley diagram is just the action diagram. It leads to a slick proof of Cayley's theorem. I recall from a long time ago that Cayley's theorem said that if G is a group of order n, then there's an embedding from G into the group of permutations on n elements, Sn. In other words, G, since this is an embedding, G is isomorphic to its image, which is a subgroup of Sn. So this is what we mean formally when we say G is isomorphic to a group of permutations. To prove this, we start by defining our group action. So the group G acts on itself, and by this I mean the set S is equal to G, by right multiplication. So because there's an action, that means that there's a homomorphism phi that sends G into the set of permutations of S, which is isomorphic to Sn, because G is a finite group of order n. And phi of G is the permutation that sends each element x to x times G. So imagine this. You have a group switchboard. Again, I always like to think of group actions as a group switchboard, and every element has a oops, let me fix that. So every element has a button. The identity has a button. A has a button. B has a button. A, B has a button. G has a button. All the elements have buttons. And when you press one of these buttons, the elements in the set S, that's just the elements in G, get shuffled, or they get permuted. So when you press the G button, every element X gets sent to X times G. That's the permutation. First of all, notice that there is only one orbit, which is the entire set, of course. And to see why this is, well, let's take an element X and let's take an element Y, and I claim that there is some way to get from X to Y, and hopefully that's clear. Well, let's think how we're going to do this. So what do we want to multiply X by on the right to get to Y? How about X times X inverse times Y? That equals Y, right? So in other words, pressing the X inverse y button is the permutation that sends x to y. So from any two elements, or between any two elements, is a path in the action diagram, meaning there is one connected component of the action diagram, which means there is one orbit. Next, the stabilizer of any x is just the identity element, because the stabilizer of x is all group elements that when you multiply x by it, you get back x. So obviously the identity is the only element such that x times g equals x. You can also deduce this from the orbit stabilizer theorem too. Remember this? That says that the size of the orbit of x times the size of the stabilizer equals the size of the group. And we just said that the only orbit is the group. So obviously this thing here is just the size of G. So clearly the stabilizer, which is a subgroup of G, must have size 1, so it must be the identity. So another way to see why this is true. Finally, the kernel of this action. Remember what the kernel is? That's a set of things that fix everything in the set. So that is always the intersection of all the stabilizers, because the stabilizers are the things that fix an individual element. So the kernel, if you have something that fixes everything, then that has to lie in every single stabilizer. So that's just the intersection of a whole bunch of singleton sets containing the identity. So that's clearly just the identity. Since the kernel of phi is just the identity, then this homomorphism phi is an embedding. And that's exactly what Cayley's theorem says. There is an embedding from G into Sn. And that finishes the proof. So this is the first of several results that we will see where we have a deep theoretical result on group theory, namely Cayley's theorem, and we prove it by setting up a clever group action that seems completely unrelated and analyzing the orbits, stabilizers, and or kernels. Because recall, we never actually proved Cayley's theorem before. We sketched the proof, and we said we needed to check a few details that technically those details involved the homomorphism property, which we had not learned yet. But we also motivated it two different ways. First, we used Cayley diagrams for how to construct the actual permutation subgroup over here, and then we used multiplication tables to construct the permutation subgroup as well. Our second example is of groups acting on themselves by conjugation. So as before, our set S is just G itself, and so we have a homomorphism from G into the permutations of S, but it's defined a little bit differently. So phi of G, meaning what happens when we press the G button, well, it's the permutation that sends X. Now, before we had X times G, but now we're going to have G inverse X times G. So the only difference is that we have this G inverse on the left right here. The orbit of X, I claim, is its conjugacy class. So let's see why. So the orbit of X is by definition the set of all things you can get to from X by pressing a G button where G is in our group. Formally, that is the set of all G inverse X G where G ranges in the group, and that's the definition of the conjugacy class of X in G. Next, the stabilizer of X is the set of elements that commute with X. That's what I claim. And this has a name. This is called the centralizer of X. Remember that the center of a group is the set of elements that commute with everything. So the centralizer of X is the set of elements that commute just with x. And let's check this as well. So the stabilizer of x is by definition the set of elements in our group G such that G inverse xg equals x. Now let's multiply both sides of this equation by G, and we get that it's a set of elements such that xg equals gx. And that's the definition of the centralizer, and we denote it as capital C sub g of x. Finally, the fixed points of phi are precisely those in the center of G. In other words, those that commute with everything. And let's see why that's true. The fixed points of phi, by definition, are the set of elements in G. Well, they're the set of elements in our set, S, which happens to be in G. So I'm going to write the set of all x in our set G, such that G inverse xg equals x for every element G in our group. And of course, G inverse xg equals x is the same thing as saying xg equals gx. And that is the definition of the center. All elements that commute with everything in the group. By the orbit stabilizer theorem, the size of the group is equal to the product of the size of the orbit of x times the size of the stabilizer of x for any element x. And we can rewrite this as follows. The conjugacy class is just the orbit, and the centralizer is the stabilizer. Thus, we immediately get the following new result about conjugacy classes. Theorem: for any element in a group, the size of its conjugacy class divides the size of the group. And let's see why that is again, in case you didn't quite see it. Well, the order of the group is the product of these two integers, the order of the conjugacy class, I should say the size of that, and the order of the centralizer. And I say order here because the centralizer is a subgroup of G. And I encourage you to prove that on your own, although it's very simple. It clearly contains the identity element because the identity commutes with x. If G commutes with x, then it's pretty easy to show that G inverse commutes with x. And also if G and H both commute with x, it's easy to see why x commutes with G times H. So this is indeed a subgroup. So by Lagrange's theorem, its order divides the order of G. However, we don't know that a priori for the conjugacy class because that's not a group. It's not a subgroup at all. Most of them do not contain the identity. In fact, every non-identity element is in a conjugacy class that does not contain the identity. So there's no reason until now to suspect why the size of every conjugacy class in the group has to divide the size of the group. So this is a pretty impressive, important result that is very non-trivial that until we studied group actions, we really had no way to tackle. And we never even saw it coming. Up to this point so far, we've seen two group actions. G acting on itself by right multiplication and G acting on itself by conjugation. Now the first one, as we said, the action diagram is just the Cayley diagram, so we've actually been studying that action throughout the course, we just hadn't called it that. So we won't do any explicit examples of that, but we will do an explicit example of the second one, groups acting on themselves by conjugation. So let's take the group D6, so the dihedral group containing 12 elements, and the orbits of this action, as we established on the last slide, are the conjugacy classes. And here they are. I think we've actually done this before in a lecture on conjugacy in the previous series. The fixed points of phi, well, by definition, these are the size 1 orbits, so they are the size 1 conjugacy classes. And recall that the size 1 conjugacy classes from the lecture when we first saw these things were precisely the elements in the center. And in this case, that's just the identity and r cubed. So these two elements are the subgroup generated by r cubed. By the orbit stabilizer theorem, the order of the stabilizer of X is the order of the group D6 divided by the size of the orbit of X. Now normally we write the orbit stabilizer theorem by putting the orbit on the left-hand side of the equation, or at least on the same side as the stabilizer, but this is clearly equivalent. So this is 12 divided by the size of the conjugacy class. The stabilizer subgroups are as follows. First of all, the stabilizer of the identity and the stabilizer of r cubed is everything. This is the whole group D6. And we can see this several different ways. So the orbits of E and of r cubed both have order size 1. So by the orbit stabilizer theorem, the stabilizer has to have order 12 because 1 times 12 equals 12. Another way to think of it is the stabilizer, remember, is the centralizer of that element. So it's a set of elements that commute with it. And everything commutes with the identity, and everything commutes with r cubed. Let's look at r next. So r is contained in an orbit of size 2. So the stabilizer subgroup must have size 6. And the stabilizer is the set of elements that commute with r. And clearly, those are the rotations, powers of r. All of these, r squared, r cubed, and so forth, commute with r. And same with r squared and r to the fourth and r to the fifth. These things are all in orbits of size 2. Their stabilizers have size 6 and are clearly these 6 elements. So these 6 elements are the subgroup generated by r, which is the subgroup C6 of D6. Next, let's look at the stabilizer of F. So F lies in a conjugacy class of order 3, an orbit of size 3, and so its stabilizer must have size 4, because 3 times 4 equals 12. So what commutes with F? Turns out that, well, obviously the identity and r cubed commute with F, but also r cubed F. Well, yeah, because the product of these two elements it's going to commute with F, and F does as well. So the stabilizer of F is the subgroup generated by r cubed and F. Next, let's look at the element Rf. That's in this orbit of size 3. So the stabilizer of this element, everything that commutes with it, well, it's got to have order 4, because 3 times 4 equals 12. So it has to contain the identity. It has to contain r cubed, because these things commute with everything. And it has to contain itself, obviously, Rf. So there's only one more element. And that's the element, well, the product of these two, r cubed times Rf. That's r to the fourth f. Now we're tempted to make r to the fourth the identity, but remember, we're in D6, we're not in D4, which is our usual example. So the stabilizer consists of these 4 elements, which is just the subgroup generated by r cubed and Rf. So both of these subgroups are isomorphic to the Klein 4 group. Finally, let's take the pattern that we saw in this example and apply it to the remaining elements in D6. So the stabilizer of r to the I times f for any integer I equals 0 up to 5, I guess. Well, as before, this has to contain the identity. It has to contain r cubed, because both of these things are in the center, and it has to contain itself, r to the if. And we know it has order 4 because both of these orbits have size 3. And so there's only one more element, which has to be r to the I times f. So this is the subgroup generated by r cubed and r to the I f. Our third example is that of groups acting on subgroups by conjugation. Notice that we can't act on subgroups by multiplication because that won't leave us with a subgroup, but rather a coset. So we will start with an example of this on this slide, and then we will generalize it on the slide afterwards. So this is more motivation. So let's let G be equal to the group D3, and I'm going to let S be the set of proper subgroups of G. When I say proper, I don't want to include D3. I can, but I think it's just easier and less confusing if the size of the group and the size of the set are different. So I'm going to have a set of size 5 and I'm going to have a group of size 6. There is a right group action of D3, of our group G, on this set S by conjugation, and it's defined as follows. So let's call it tau, and tau sends D3 to a permutation of S as follows. Tau of G, in other words, pressing the G button, what permutation does that yield? That's the permutation that sends each subgroup to this conjugate, G inverse H, G. Turns out that this is a right group action, and there's an analogous left group action if you put the inverse not here on the left, but on the right element. Here is a picture about what each of these permutations look like. So pressing the E button, the identity button, fixes this entire set. If you press the R button, then these two subgroups are preserved, and these three subgroups cycle like this. Notice that this subgroup generated by R is fixed because it's normal. If you conjugate it by anything, you get back itself. But F is not normal. If you conjugate, when I say F, the subgroup generated by F, if you conjugate this subgroup by R, you get this subgroup generated by RF. So this is not normal, and likewise, these things form a 3-cycle. Tau of R squared. If you press the R squared button, then this is the permutation that ensues, or that results. Tau of F. So let's conjugate by F. So obviously, the subgroup generated by the identity, the trivial one, is normal, as is the subgroup generated by R. That's normal. But also here, even though the subgroup generated by F is not normal, if you conjugate that by itself, I mean, like, let's do it down here. If you take this E and F, this subgroup, and you do F inverse, which is just F times F, in other words, this is the element F, E, F, which is just the identity, and then F, 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 which is just F. So that's the same subgroup that you started with. So conjugating this subgroup by F actually fixes it. But it does not fix either of these two, it transposes them. And the other two reflections are similar. Pressing the RF button swaps these two subgroups, but fixes this one. And pressing the R squared F button is going to swap these two subgroups, but it fixes the one generated by itself. On the right is the action diagram. So the identity, or the trivial subgroup, is fixed by everything. It's fixed by R, and it's fixed by F. Same with the subgroup generated by R. That is normal. So if you conjugate it by R or by F, you get back itself. And then the other three subgroups, the non-normal ones, look like this. So conjugating them by R creates this 3-cycle, and if you conjugate them by F, well, that's going to fix this one and swap these two. Now, just as an exercise, I said, let's let S be the set of proper subgroups. And I mostly did that because I wanted this set to have size 5 and this one to have size 6. But what would happen if we included the full subgroup D3 in here? What would that look like in the action diagram? Well, D3 is normal, so that would be a fixed point. And R would fix that, as would F. So we just get another fixed point. And that's another reason why I didn't include this, because I didn't feel like it was necessary to have a third subgroup that is fixed by everything. Let's now compute the stabilizers of each of these subgroups. In other words, each element in S. So these two fixed points, because they're fixed points, they're stabilized by all of D3. Everything fixes them. And if you think about what a stabilizer means in this context, it's the set of all group elements G that normalize H. So the stabilizer of this is just the normalizer of that subgroup in D3. And the same thing holds for the other subgroups. The stabilizer of subgroup generated by F is all things that normalize this subgroup. And you can read it off the action diagram. The identity path starts here and ends here. And what else starts here and ends here? Well, F. So that normalizes this subgroup. And you can say, well, there's also R cubed, but that's the identity. There's also RFR, but that's also just F. So the stabilizer of this, well, it's got to have order 2 by the orbit stabilizer theorem. The orbit has size 3, and the group has size 6, so the stabilizer must have size 2, and here it is, the normalizer of the subgroup. Next, the stabilizer of RF also must have size 2, but it doesn't have to be the same, and it's not the same. So what are all paths that start here and end up here? Well, there's the identity, obviously, right? But then there's also RF, red, blue. So these two elements, or this subgroup, is the normalizer of the subgroup in D3. And notice that the normalizer, because these groups are not normal, it can't be the entire group, because that only happens when the group is normal. But it has to contain itself, and there's nothing in between. There's no subgroups in between this order 2 subgroup and this order 6 subgroup. So the normalizer has to be itself. Finally, the stabilizer of R squared F is the normalizer of R squared F, which is itself. And you can see that because the identity starts here and ends up here, and so does R squared F. Let's summarize what we just did and apply it to general groups. So if we have an arbitrary group G, then it will act on its set of subgroups S by conjugation, just as we defined before. And here we can include the entire group as a subgroup if we want to. So phi is a homomorphism from G to the permutations of the subgroups of G. And if you press the G button, then that's the permutation that sends each subgroup to this conjugate G inverse H G. This is a right action, but there's an associated left action, as I mentioned before, where you just put the inverse on the rightmost G. Let's take an arbitrary element of our set, which is going to be a subgroup of G, and let's try to understand the orbits, stabilizers, and fixed points. The orbit of H consists of all conjugate subgroups. So the orbit of H is the set of all G inverse HG, where G is an element in our group. So it's a set of all subgroups that you can get to by conjugation. The stabilizer of H, as we've noticed, is the normalizer of H in G. And we can see that explicitly. The stabilizer of H is the set of all elements in our group such that G inverse HG equals H. And that's exactly the definition of the normalizer of H in G. Finally, the fixed points of the action are precisely the normal subgroups of G. So the fixed points of phi are the set of all subgroups of G such that G inverse HG is just H for all group elements. And that's exactly what it means to be normal. Let's say a word or two about the kernel of this action. So the kernel is everything in the group that gets sent to the identity permutation. In other words, every element whose button fixes every single subgroup. So the kernel of this action is the entire group G, is everything, meaning this map is the trivial map, if and only if every subgroup of G is normal. If every subgroup of G is normal, then every point is a fixed point, and so the kernel is everything. And we've seen a few subgroups we've seen a few groups that have this property. Any abelian group has that property. The subgroups are normal. And even a few other groups. I think the quaternions was an example, Q4, of a group where every subgroup was normal. In this case, phi, as I said, is the trivial homomorphism. So pressing the G button fixes or normalizes every subgroup. For all other groups, if you have subgroups that are not normal, then there are going to be elements that don't normalize every subgroup. And so those elements are not going to be in the kernel. But in general, the identity element obviously is in the kernel, but so is the center of the group. The set of elements Z of G that commute with everything, that has to be in the center. So the kernel is going to be at least the center of the group, and at most the entire group. Finally, we come to our fourth and last example, and arguably our most complicated one. And this is where groups act on cosets of a subgroup by right multiplication. So let's fix a subgroup H of G. Then G acts on the right cosets of H by right multiplication. So here is the homomorphism. And pressing the G button, so phi of G, is the permutation that sends each right coset hx to hx times G. Okay? So first of all, there's a obvious analogous left group action where you send left cosets to left cosets. Just put these things on the other side. Next, let's take an arbitrary element of S. So that's going to have the form h times x. And here by G mod h, I'm going to let this denote the right cosets of H. And so that is our set S throughout. First of all, there is only one orbit, always. For example, given two cosets, hx and hy, there's always a way to send this coset to that coset. Well, how do we do that? Well, if we start with hx and we want to get hy, we just multiply on the right by x inverse y, and the x's cancel, and we're left with hy. So in other words, pressing the x inverse y button sends hx to hy. Secondly, the stabilizer of hx is the conjugate subgroup of, in particular, this conjugate subgroup, x inverse hx. And let's see why. So the stabilizer of hx is by definition the set of elements in G, the set of all little g, such that hxg equals hx. Now, if we move this x to the other side and make it an x inverse, we can write this set as the set of all group elements, little g, such that this right coset, h x little g x inverse, equals h. And I claim that this set of elements is actually this conjugate subgroup, namely x inverse hx. And that's not clear. So let me box this, and I'm going to sketch the proof of this. I say sketch the proof. I'm going to prove it. I'm just not going to write it up in complete sentences. I will let you do that as an exercise, if you so choose. So several observations. So because we are trying to prove that two sets here are equal, then we have to show that one of them is that the left-hand side is a subset of the right-hand side and vice versa. In other words, we take an element from the left-hand side and show it's in the right-hand side and vice versa. So the last observation I want to make is if these two cosets are equal, then this representative xg x inverse has to lie in H. So this has to lie in H because this right coset has to actually be H. So this thing representative has to be in H. So let's start with the proof. So first of all, let's do the first containment. Let's take an arbitrary element in the left-hand side and prove that it's in the right-hand side. So let's take G in our group such that x G x inverse lies in H. Now what we have to do is we have to show that it is in this conjugate subgroup. In other words, we have to write G as x inverse times something in H times x. So how are we going to do that? So G, let me write that, then G equals x inverse times something in H times x. What should go right here? What's the something in H? Well, how about this? That's perfect. X G x inverse. And clearly that's equal to, clearly this is equal to G. These cancel and those cancel. And clearly this is an element of x inverse hx. So that confirms that part. And now let's do the reverse containment. Let's take something in x inverse hx and let's show that it is in the set. So let's take, let me call it something. Let me call it G it equals x inverse hx. So I'm taking an element in x inverse big H x. So let's call that element x inverse little hx. In other words, it's that product. And let's call that product little g. So now we are trying to show that this particular element, g, this particular element, satisfies this property. So then, in other words, to show that this is in, show that g, well, let's write it then. G, or x, g, x inverse, we are trying to show lies in H, right? That's all we have to show, is that x, g, x inverse lies in H, because then this right coset will be equal to H. So let's write it out. X, g, x inverse equals x, well, what's g? G is x inverse hx times x, and that's clearly equal to H, which is in the subgroup H. So there we have it. Both of those were pretty much straightforward. They had to do with the fact that here we're conjugating by x, and then we conjugate by x inverse, and so the x's are going to cancel. So these two sets are indeed equal. So the stabilizer of hx, which by definition is just this, we rewrote as this, and then we claimed and proved that that is just this particular conjugate subgroup of H. Finally, let's say a word or two about the fixed points. So let's assume that our subgroup H is proper, because if it's the entire group G, then the action is very trivial because there's only one coset. So assuming H is indeed proper, there are no fixed points of phi. Well, why is this? Well, fixed points are just orbits of size 1. And we've already established that there is only one orbit of the action. So there can't be other orbits of smaller size. And this only orbit, because it contains every element in our set is G mod H, the right cosets. How many right cosets are there? Well, there is this many, the index of H in G. That's the definition of index. And that, because H is proper, is greater than 1. So the orbit stabilizer theorem, let's just verify that that indeed holds here, is the order of G is the size of, let's just take an arbitrary orbit, an orbit containing the element hx. Well, there's only one orbit, so it doesn't matter what representative I use for it, times the size of the stabilizer of hx. And so the size of the unique orbit is the number of cosets, which is just G, or the index of H in G. And the size of the stabilizer, well, the stabilizer is a conjugate subgroup of H, so it has to have the same size, because remember these things, this is isomorphic to H. So that's just the size of H. So we get that the order of G, so we just get Lagrange's theorem. The order of G is the index of H and G times the order of H. Finally, the kernel of this action is, as always, it's the intersection of all of the stabilizer subgroups. And since the stabilizer subgroups are conjugates of H, the kernel of this action is the intersection of all conjugate subgroups of H. So it's this intersection right here. Finally, I claim that the kernel, well, it obviously contains the identity, but I claim it is a subgroup of H, and it's equal to H if and only if H is normal. Now let's draw a picture to see why that's the case. So H is some subgroup, it's like this. And then the kernel is the intersection of all conjugate subgroups. So the other subgroups might look like this. There might be one there, there might be one there, there might be one there. So this might be X inverse H X. This might be Y inverse H Y, and I'm not going to name the other ones. So the kernel is the intersection of all of these. Clearly the intersection of all of these things, since H is one of them, has to be contained in H. It can't be any bigger because we're intersecting things. So that establishes this first claim. And secondly, the kernel is all of H if and only if H is normal. Well, if H is not normal, then we're going to get some of these subgroups which do not lie in H, which are different, and the intersection will be smaller. But if H is normal, then all of these subgroups are actually H. So when we intersect them all, we just get back H itself. In other words, this picture happens when H is not normal, and when H is normal, every single one of these conjugates is H equals X inverse H X equals Y inverse H Y, etc. And the intersection is equal to H. And so that's the kernel.